Okay, so last time we kind of talked about some ways that we can actually concentrate materials to actually mine it for different purposes. So we talked about different minerals that we can actually get out of sedimentary processes because of the sorting process, right? Because the mineral will actually accumulate or concentrate in one place, we can then use it for mining. So like chromite is actually a heavy metal that we can actually mine for chromium, we can use for stainless steel. Rare earth oxides, we talked about this when we talked about phones, so it can be used for fiber optic cables, magnets, for lots of electronics. Diamonds, copper, gold, platinum, these are all heavy metals that can be extracted from sand deposits lots of times where they will be concentrated, right? So these sediments, we've talked about the actual process here where we talk about weathering first, then erosion, then transportation, then deposition. Well, after these sediments get deposited, they can then become what we call lithified. And we'll talk about the examples of that. So for example, if a sediment like gravel gets lithified, it can turn into what we call a conglomerate. If sand gets lithified, it can turn into a sample that we call like sandstone. Okay? Or like muds or clays gets solidified, it can then form into what we call a shale. So each one of these, after lithified, we call it a different rock. So when we classify rocks, we classify it by either being a chemical rock or a clastic rock. Clastic meaning that it has particles that you can see, whereas chemical means that it came from some chemical process. So these are often mechanical weathering processes for the clastic rocks, and these are often chemical processes or chemical weathering processes for the chemical rocks. So here's some examples of some. So clastic rocks are usually classified based off of size. The smaller stuff is usually shale, then it goes up to siltstone, which is the next smallest stuff, then to sandstone, which is the next smallest, and then we do it into what we call conglomerates or breccias. And I put a chart on our discussion board to help you classify rocks when you do your discussion board, by the way. That might help you classify these a little bit better. In class, if I had a class, what we would do is we'd get rocks out at this time frame and let them look at them and help them to try to actually sort them in this way. And that's what we're kind of doing in our discussion board this week. It's the best way I can think of to do it with the short resources we do on an online setting, right? So, but anyways, so for chemical rocks, you might have things like rock salt or gypsum rock that is chemically derived from an inorganic setting. Often when you have what we call evaporites, which means that you might have water that has lots of salt in it and it slowly evaporates away, leaving behind the rock salt, or maybe even a lot of sulfur and magnesium in it, so it's going to leave behind gypsum instead. You can have plants that actually break down and get compressed, which is a chemical process, and you can form coal. You can have silica in it that is dissolved in the water, slowly harden, which we can call chert. We can have calcite, which will actually slowly harden and to form what we call limestone. And then there's special types of this limestone or dolostone. Dolostone just means it's magnesium rich, and limestone means it's calcium rich. And then you have things like coquina, which is a bunch of shells cemented together, or phosphorescent limestone, like that one I showed you here, which is a coral that is now cemented together. Right? So these are some examples of some of these, and we'll show you some of these over time. So this process in which the sediment becomes that rock can happen in two ways. So the whole process of it is called lithification or diagenesis, which is the cause of either physical or chemical changes to a rock, okay, to lithify it or cement it together. So compaction is just the actual process in which the material above it pushes down on it, pushing the materials closer and closer together to pressurize the material. Now, if you put so much pressure on it, it can actually fuse the materials together because of all the heat generated by the pressure or the force of that sediment over time. Whereas cementation is the process in which the sediments are bound together, because as water flows through this, there's ions in that fluid and are precipitate together to form a kind of a cement. So, for example, this is a calcite cement in the middle of these sand grains, or you can even have silica cements inside of the sand grains. Okay, so the last thing that can happen in a chemical rock, or we're going to start talking about chemical rocks a little bit more. We've just kind of focused on clastic rocks prior to this, is through the crystallization process. So as something dissolves, evaporates away, you're going to get like gypsum or halite to form kind of the rock itself. Okay, or you can always have something that we call recrystallization, where you have something that actually gets recrystallized. So here's an example of one. This is a fossil fish, where the bones of that fish itself have been slowly decayed away and have been replaced by other minerals, right? It still keeps the kind of form of the fossil because that it's tends to be harder than the other minerals because the chemical process is reacting with the fossil, and so you end up with a recrystallization of materials. So a good example of this is petrified wood. I have an example of that right here. You can see the different petrified wood here, where it looks like the actual wood grains, but it's actually been the organic material has been replaced by silica and other minerals. Okay, so chemical sediments here are important in mining as well, in mineral resources, because usually when we dissolve that material away, we can then use that material for things that we use every day. For example, halite or salt. We can do that all the time. Okay, so for example, these are some of the minerals that we often will get from chemical processes. We can get gibbsite, which is a commodity that we use for aluminum lots of times. It's usually the chemical weathering of aluminum-rich rocks or something like that, and we'll start solidifying over time to form gibbsite. Goethite, which is often caused by has a commodity of nickel and even iron, depending upon the concentrations. And you can even get clay minerals, which we use for ceramics, cat litter, paper, things like that all the time. Okay, so some minerals are more soluble than others. Remember, quartz is really stable, so it won't dissolve, whereas other minerals like calcite is much more soluble, and halite is even more soluble, right? Salt, you just put it in the water, it's going to dissolve away. Those chemical bonds are very weak, and so they actually will dissolve. Whereas calcite is a little bit more, will dissolve slower because it's a little bit more stable. But if you put an acid on it, it will slowly go away. Now, I wish I had some of my hydrochloric acid. If I put hydrochloric acid on it, it's a weak acid that if you put it on my limestone like I have right here, it will actually bubble and effervesce. Basically, the carbon will come and the oxygen come out of the rock itself, the calcite, which is calcium and carbonate, and CO2 gases will be emitted, right? So it'll fizz and bubble. And that's one of the main ways we figure out if a rock is chemical or has calcite in it, is by doing that what we call an HCl test, a hydrochloric acid test. Okay, and if you look in your discussion board, you'll see some examples of that. So these different minerals will dissolve at different rates. Calcite, if I get a small sphere of calcite, it will actually dissolve within fairly quickly, right? Okay, and so this is the time it would take a 1 millimeter sphere of this mineral to dissolve in water with a pH of about 5. So calcite, it would do it in about a month or less. Okay. Whereas olivine, which is one of my favorite minerals, it's going to take almost 2,300 years for that to dissolve away. Whereas quartz, it's going to take almost 34 million years for it to dissolve away. So it's very resistant to different things. Okay, so that's important. Now, different minerals are going to dissolve have different reactions to those chemical materials. Okay, so for example, if we have a composition of some freshwater lake, like for example the Great Salt Lake, it has. The Great Salt Lake is what we call a closed basin, where all the water is coming down into this one lake, leaving all the salts and stuff like that in the water. So as it evaporates, it leaves behind the salts, okay, like the halite. And so you'll have high quantities of chloride and sodium, because that's sodium chloride or salt. But it also has stuff like sulfates, magnesium, calcite, and stuff like that. So the average seawater might have 19,350 milligrams per kilogram within that water. Well, the Great Salt Lake has a lot more. Okay, notice that it has it's a lot saltier than the ocean water. Okay, whereas an average just rainwater might have hardly any materials in it as well. Whereas the Mississippi River might 24 milligrams per kilogram. Right, and so different waters are going to have different concentrates. So if the Great Salt Lake evaporates away, it's going to leave a lot of salts behind. If the ocean does, it's going to do the same. If my river water from maybe the Mississippi, you're not going to leave much behind, right? Because it has a different concentration of this material within that fresh water. Okay, so here's an example of a quarry. This is a limestone quarry in Illinois, where you have that calcite basically slowly precipitating at the bottom of maybe of a shallow sea, and then we now can mine it and to extract that material. And that calcite we use in cements all the time, in toothpaste, in a lot of different things, because that calcium gives our calcium for our teeth and our bones, stuff like that. So we use calcite in a lot of different things, a lot of times in cement, but one of the main things. And this happens in places where we have high evaporation rates, like in the Great Salt Lake, right? That's why we have the salt flats out there, or if you've ever seen the movie Pirates of the Caribbean, where Jack Sparrow is taking that boat across that big white plain, right? That's the salt flats, where all that salt from that Great Salt Lake is slowly dissolved, evaporated away, leaving behind these really white plains of salt. Same thing happens in the Dead Sea. Well, it's also going to happen in places where you have shallow marine environments, like the Bahamas, right here, right? Okay, where you have the shallow sea here, where the limestone or the calcite can slowly solidify out to form limestone over time. So here's some examples of some of these inorganic materials that we can mine, like limestone and dolostone, which we can get for cement, rock gypsum, which is for drywall, and rock salt for foods, de-icers, things like that. Banded iron formations, and I have an example of one right here. This is a chemical rock as well, and where the materials are basically being precipitated out and getting all the iron out of there and forming these iron deposits. And this is where we get a lot of our steel from today, and that happened a long time ago. Okay, we had a lot more iron in our waters. Now, other things we can do is what we call biochemical reactions, and this is when animals actually help the chemical process, okay, to form like corals, coral reefs, and shells, and things like that. Okay, so now what's very important about biochemical sedimentary rocks is these biochemical sedimentary rocks also tend to form what we call fossil fuels: oil, natural gas, coal, all biochemical sedimentary processes to form these things. Coal is that sedimentary rock that forms from the compaction of plants, okay, and it forms that shallow burial and compaction of the peat, where you have the chemical processes slowly changing that peat to other materials. So here's some of the major coal fields in the United States where we get our coal from, like the West Virginia has the Appalachian coal, Central Appalachian coal. We don't really have much in North Carolina at all, but all along the Appalachians, Texas, the western and eastern interior, and then we have lots out here in the western United States. And this is where we get a lot of our coal today out here in Wyoming, because it tends to be a lot cleaner coal than the stuff in West Virginia. This has a lot more sulfur in it, so when we burn it, you get a lot more acidic acids and acidic rain, whereas this one here is a much cleaner coal. And so now coal, slowly over time, will form from this organic material. So you'll start off with maybe some lignite, which I should get that. I have some examples of it here that we can find here in our neck of the woods. Below us, sometimes we'll have wood that actually get in those sand deposits, and the wood will slowly become carbonized and form into lignite, which is a brown coal. It's soft and crumbly. And then it slowly over time, as you continue to compact that coal over time, the impurities will come out of it, and you'll get a much cleaner coal. So, for example, anthracite is a clean coal that we can get from up near Pennsylvania, and it's burns with less carbon emissions than maybe a lignite would, right? And then petroleum is also a biochemical process, and this actually occurs from those organisms that are living in the ocean, and slowly will solidify at the bottom, and then will get compacted over time to form oil. And then sedimentary rocks might get deposited on top of it to trap that oil or that gas, and then we can get that oil and the gas out over time by drilling or fracking is an way we can get it out of shales, or from natural traps like we see in this picture here, right? And we don't have time to talk about all the negative impacts of fossil fuels. Fossil fuels are absolutely necessary for our economy, but we also are trying to lower our use of fossil fuels to limit the global warming impacts and things like that. And if you're interested in stuff like that, I have a whole other class called environmental geology where we focus just on that, right? And so I think we're break for today, and we'll not just for today, but for this segment, and we'll start again in just a bit.